All right, so I assume we will have more people joining. But let's get started. So good afternoon, everyone, and welcome to the IFAS AI and Data Science Seminar Series. I'm Chang from Agronomy, and I will be the moderator today. So it's my great pleasure to introduce our speaker, Dr. Rattan Lal, who will be presenting on farming carbon and advancing sustainable development goals. So today's seminar highlights how agriculture and soil carbon dynamics are central to both the challenges and solutions of climate change and the global food security. So it's truly an honor to introduce Dr. Rattan Lal. Dr. Lal is a distinguished university professor at the Ohio State University and the director of the Lal Carbon Center. He's widely regarded as one of the world's leading soil scientists and a pioneer in soil science, soil carbon sequestration, and regenerative agriculture. Over his remarkable career, he has authored about 1,200 journal articles and mentored more than 430 researchers for around 60 countries. His contributions have been recognized with numerous prestigious awards, including the World Food Prize, the Japan Prize, and the Glencore World Soil Prize. Dr. Lal's work has fundamentally shaped our understanding of how soils can be part of the solution to climate change, food security, and sustainable development. So before we begin, just a couple of quick notes. This is an 1 hour seminar, including time for questions and discussion. So please feel free to put your questions in the chat throughout the talk, and I will help moderate the questions at the end. So with that, it's my great pleasure to welcome Dr. Lal, and thank you for joining us today, and the floor is yours now.
Thank you very much for the very kind introduction, and it's a great honor to be invited. I had very much hoped to come and visit there. I hope it may happen sometime in the future. I'm not too much knowledgeable about AI, but I have a couple of students who are evaluating soil organic carbon by remote sensing techniques and without bringing soil sample to the lab. But I am going to talk primarily about what the title is, farming carbon, what it is, what it implies in terms of relation to soil health, and how it generates numerous ecosystem services, in which part of the Sustainable Development Goals of the United Nations. So it's really a great pleasure to be able to discuss this important topic with you. So let's look at the carbon cycle on a global scale. Different types of carbon which move from one reservoir to another reservoir. Atmosphere is, of course, the main player in the global carbon cycle and a big factor in climate change. And the carbon in the atmosphere is called gray carbon. And this gray carbon is increasing because of the fossil fuel carbon called red carbon is being emitted every year, about 10.4 to 10.5 gigaton of carbon from the fossil fuel combustion. Then there's a green carbon, and the atmospheric carbon is absorbed by plants through photosynthesis, and that is what we call green carbon, which is the mechanism to reduce the CO2 concentration in the atmosphere. Then we have carbon, which is called brown, which is a soil carbon. Soil is the largest reservoir of carbon. It has two components, organic and inorganic, and the respiration of carbon from soil goes back to the atmosphere, and of course the green carbon become humus when it is mixed with soil or returned to soil through input of biomass. Then we have blue carbon, that's the carbon in aquatic ecosystem, including ocean, streams, river, lakes, etc. Irrigation water is, of course, converting green carbon for increasing photosynthesis in the arid climate. I mentioned there are two types of carbon in soil. One is humus, organic. The other is inorganic carbon, that's carbonates and bicarbonates, and that generally is called white carbon. And there is, of course, an important carbon, black carbon, which is charcoal essentially. And these days, charcoal and biochar are very important components as soil amendment as well as source of energy. And carbon cycles from these different reservoirs by human activities, this has influenced tremendously, and that has created some environmental issues, including abrupt climate change. The question is how to use green carbon, how to increase green carbon production so that we can take CO2 from the atmosphere and minimize the risks of global warming. Now, the CO2 in 1960 was 315. In 1750, Industrial Revolution era, it was only 280. It's going up tremendously. 416 in 2020, 2022, 418. And this morning I checked, is 432 parts per million. So it's increasing rapidly, and hopefully it will not get to double than what was pre-industrial era. But the sources of carbon into the atmosphere have been land use as number one factor. The land use became a source of carbon about 3,000 years ago when the agriculture began. So prehistoric time, from the beginning of agriculture to about 1750, the estimate is that 320 gigaton came from land, conversion, drainage, deforestation, biomass burning. And then from 1750 to 2024, that's last year, the data is not available for 25 yet, 280. So together, an approximate estimate is that 600 gigaton of carbon have come from the beginning of agriculture till today from land use change and land use conversion. Let's compare that with fossil fuel combustion. It's a much more precise information. From 1750 to 2024, the estimate is 500 gigaton of carbon. Therefore, the cumulative total from 1750 to now, about 780 gigaton total, is 64% from fossil fuel and 36% from land use change. The atmospheric temperature has already changed. This number 1.1 should be updated to 1.2 or 1.3. It's going up rapidly. And these emissions have and will continue to affect the ecosystems from which we derive food, feed, fiber, fuel, water, biota, shelter, and many other ecosystem services. So understanding this global carbon cycle, also national carbon cycle at a state level or a county level and a farmstead level. As you get to the farmstead, it's become a little more complex. Global is more easy to calculate, but this information is very vital. The question that many times is asked, how much carbon can humanity burn, emit, release into the atmosphere before the global warming becomes severe issue? So I call that a carbon pie. So let's say that doubling the carbon dioxide from the pre-industrial era, which are 280 parts per million, is really the tipping point. So 560 parts per million minus what is today, as I mentioned already, 432 parts per million. The difference of the two, if you multiply by 2.1 gigaton of carbon for each parts per million in the atmosphere, that's about 269 gigaton. And if we are burning every year 10 fossil fuel gigaton of carbon, that means we have about 27 years of fossil fuel liberty to burn so that the temperature does not exceed beyond irreversible issues which become the problem. So the question is, if it's 260, 270 gigaton, maybe less 250 gigaton, because also land use part should be included in this calculation. How should this 270 gigaton be divided amongst all nations of the world, amongst all people of the world? And how can biofuel part be a possibility to substitute, so to say, in terms of minimizing the risk of global warming? Now, the other part is sustainable development goals. So that's the carbon part, what carbon is, what are different types of carbon, what the emission has been happening from anthropogenic issues, activities. Sustainable development goals, one can look at those which are directly affected by soil health, such as goal number 2, end hunger, goal number 3, climate action, goal number 13, climate action, goal number 15, life on land. And then there are some secondary sustainable development goal. Number 1, and poverty. Obviously, if agriculture is improved, rural poverty and related industry would have impact on poverty. And then number 3 is good health. Number 6 is clean water. And number 7 is renewable energy. Directly and indirectly, there are at least 7 development goals which are directly impacted by soil health. I must say that in spite of all this, the word soil health does not appear in any of the sustainable development goals. Land does, but not soil health. So hopefully this can be corrected in future. Now, the third part, farming carbon. We have defined what is the global carbon cycle, what the sustainable development goals are, how they are connected to carbon and soil health. And now, what is farming carbon? It means a set of agricultural practices adopted under site-specific conditions to remove CO2 from the atmosphere and to transfer it to land-based sinks. And these are soil, above and below ground biomass, and these can reduce emissions of greenhouse gases, all 3 of them, CO2, CH4 and N2O, and the rate of estimation of storage of CO2 on a permanent basis with mean residence time long can also facilitate the process of earning revenue for land managers. So transferring carbon from atmosphere into land, soil and biomass, so that that carbon can bring some additional income as well, in addition to many other services. In a way, if you want to put it that way, because it's growing carbon in land, it brings income. So can farming carbon be a new crop, like that of wheat or rice or cotton or sugarcane or salmon? Well, similar to those crops, carbon can be a new crop with its specific practices to enhance its stock and manage its flux. What are the benefits of carbon farming? Adaptation, mitigation of climate change, abrupt climate change or anthropogenic climate change, restoration of soil health and non-soil health, all the environmental components, production of more and high quality food and feed. And I must say high quality means nutritional quality. The nutritional quality should not be diluted by increasing production. They are both important. Generation of farm revenue and conservation of soil and water, creation of high activity and species diversity of soil biota, which are very important for managing soil health. And of course, all of these are related to ecosystem services that I mentioned before. There are some other advantages as well, but these are some important ones. And in a way, carbon farming is a holistic farming approach. What it means is we got soil amendments, both organic and inorganic and others. We have conservation agriculture, which has several pillars. Some people think it's 3 pillars. Other people think it's 5 pillars: no-till, residue management, cover cropping, integrated pest management, integrated nutrient management. That's all put together called conservation agriculture. Then it's integration of crops with trees and livestock, agroforestry, a very important part. Dr. Nair is with us today, is number one on agroforestry issues. So all these interacting together and raising carbon content stock in the land is carbon farming. That's what I mean by growing carbon. And this growing carbon leads to several ecosystem services. And if we somehow can estimate the social value of carbon, how much is the revenue that can come from it? And economists define that social value in a different way than perhaps agronomists would define. Agronomists define social value in a way of how much money is required to produce 1 ton of carbon in soil. Crop residue, the cost of that, maybe the land rent, maybe the additional NPK and amendments required, their cost to produce 1 ton of additional carbon in soil. Economists believe that it is the damage done by 1 ton of carbon if it's released into the atmosphere. So, anyway, they both are related but not exactly the same. And of course, the payment for ecosystem services. And I mentioned here payment for ecosystem services. I didn't mention carbon credit. The reason is until the market mechanism is fully developed, the payment to farmer in a way which is fully justified in a transparent and a manner in which the farmers are rewarded have not yet developed. In the meantime, we should pay farmer for the ecosystem services which is being produced by growing carbon in land. So that's the difference between the two. What are the challenges of carbon farming? And I think this is where AI can play an important role by facilitating the choice of practices through better scientific data, through collation measurement analysis, and assessment of carbon credits, which will require also AI. And carbon credits means organic, inorganic, biomass, above ground, below ground. All of those verification, again, AI would play a very important part in measurement, monitoring and verification, and evaluating permanence, mean residence time, calculating the social value of carbon, and of course, the time factor, evaluating how long before carbon that is being put into the land can actually be monitored. Some people talk about it takes time before it's built up. And all of these things can be facilitated by a holistic approach, which definitely has to involve policy, education, outreach, commodification, system of payments to farmers, and all those things. Education, I must say, there are a couple of books that came out, one in Spanish. It's called Agreement, published by Institute for International Cooperation in Agriculture at Costa Rica. It's a very nicely cartoon book for children, education about agriculture and carbon farming, about soil health and so forth. And I'm pleased to say one just came out in Hindi. And this one is each alphabet has focus on soil, climate, environment, agricultural practices, and so forth. We need more of those languages so we can attract best and brightest children to agriculture, to environment, to soil health management, and so forth at a very early stage. And of course, all these things also have to be scaled up from a small scale, or hopefully eventually to a global scale. What are the impacts of carbon farming? Create a resilient agro-ecosystem is one impact. Enhance soil health, of course. Restore land productivity and reduce emission of greenhouse gases. These are the benefits which I've already mentioned. The basic technique of carbon farming, I already mentioned a whole farm approach. And this whole farm approach has different components. We got crops, we got trees, we got livestock, and then, of course, we got to improve forages, potential rotational grazing, which have a tremendous potential of storing carbon in soil, sometimes more than in croplands. Trees, of course, is an important component, especially woody biomass above ground and below ground. And in terms of crops, they can be, of course, grown by conservation agriculture, cover cropping, integrated nutrient management, complex farm rotation. Together, combination of all this can give us many site-specific techniques which should be validated and adapted. The goal is complex agro-ecosystem, agroforestry system, silvopastoral system, agro-silvopastoral system, and eventually we want to transform agriculture from being a problem, which many people unfortunately think, to a part of solution. That's the goal, transforming agriculture from a part of the problem to be very integral to be a part of the solution. But the process of farming carbon, we want to remove CO2 from the atmosphere by growing crops of economic importance. We want to evaluate both soil inorganic carbon and soil organic carbon. In this case, the AI could really be very, very beneficial. Right now, monitoring carbon in soil is very laborious, time-consuming, and expensive undertaking. So AI hopefully could provide quite a lot of improvements in our assessment methodology. We also should consider emissions avoided by better agriculture practices, all greenhouse gases, CO2, CH4, and N2O, and the plant biomass, of course, measurement and its evaluation, ground cover, what kind of components, detritus material above ground, below, how deep is the root system, and does the deep root system lead to better soil carbon profile? Right now, organic carbon is concentrated close to the surface, where it's subject to climate, activity, flowing, and can be mineralized, returned back to the atmosphere. If it's deeper in the subsoil, its residence time can be longer. And this rate of change of carbon stock, which is called carbon farming, should be assessed in megagram of CO2 equivalent per hectare per year. Megagram is, of course, metric ton, and the CO2 equivalent convert N2O and CH4 also by using their global warming potential value equal to CO2. The global warming potential of CO2 is 1, of CH4 is about 25, and N2O 300. So convert everything back to CO2 equivalent. And then we use the stored carbon as a farm commodity which can bring income for farmers. And that will make this whole process as carbon farming. One other part which is very important to understand and probably use some practical application of it, soil is a living entity. Many people think no, soil is not living, but it's a habitat for living organism. Whatever you might consider, soil definitely has attributes of a living entity. If a soil is dead, I mean the living organism cannot survive in that soil, the ecosystem services cannot be produced. The use efficiency of input, fertilizer, water, energy, other thing, even the so-called tremendous potential of improved varieties cannot be realized if the soil is not a living entity. The soil health, and the word soil health mean health only apply to living things. Health does not apply to anything else. So soil health mean soil has to be considered, treated, used as a living entity. And then making soil and agriculture a solution to global issue. Soils of managed ecosystem with crops, pasture, forest, urban have a large carbon sink capacity.
I think Dr. Lal is frozen. Can you hear us?
Looks like it.
Yeah. Hopefully he will be back soon.
So soil.
Yeah, there's some connection issues there.
Like we lost him altogether. Oh, there you
Okay, great.
And Molly can fix this in the video later. When you send it to her, just letting you know.
Sure. Dr. Lal, you are muted.
How long was I muted?
Like 30 seconds. That's fine.
Oh, okay.
Yeah.
So let's share the screen again then. Okay. I do not know how it happened. Can you see anything?
Yes. Yeah.
Okay.
Nice. That's good.
All right. So I got to go back to where I was, living soils. That's where I don't know how I got muted. Okay. Living soils, the soil is a living entity. And that's where soil health term is used because only living entities can have health. So the global warming, human activities have raised atmospheric CO2 by 54.3% since 1750, from 280 to 432 parts per million as of today. So that is an increase of 54.3%. The average temperature has increased by approximately 1.5 degrees centigrade. There's a range between 1.2 and 1.5, but it's always difficult to estimate exactly. But 2 degrees centigrade can happen if we do not change our source of energy. And that means very rapid warming, leading to rate of increase from 0.1 degrees, which is a normal, to about 0.2 degrees centigrade per decade. And that is global warming. Global warming is when the rate is almost double that under natural condition. And food systems have certainly contributed 1/3 of total warming. Food system. Agriculture is the beginning of the food system. There are many other steps part of it. That's 1/3. Soil health. As I mentioned, soil's capacity as a dynamic and biologically active entity within natural managed landscape to generate many ecosystem services. And input of biomass is critical for maintaining and restoring soil health. A healthy soil should look like this. Lot of roots, lot of living organism, earthworm, termites, centipedes, millipedes, macroorganism, meso, micro, all of them. And soil and life are very intricately interconnected. Charles Kellogg, he said there can be no life without soil and no soil without life. They have evolved together. I would like to state that rhizosphere, that is soil root interface at a nanoscale, is the only place in the universe known, proven, where the death is resurrected into life. The plant and animal remains are converted into mineralized, decomposed into minerals, releasing nutrients absorbed by plants, and the life begins again. And on this soil health depend many ecosystem services, which I've already explained: water, climate, food, biodiversity, and many others. Soil health, indeed, the engine of economic development. One part which finally I want to discuss, what is the optimum level of soil carbon in the root zone? And it depends on the crop, depends on the climate, depends on the site-specific situation. In the temperate climate, Midwestern United States, the value for the root zone top 30 centimeter is about 2.5% of organic matter content, which is organic carbon content of about 1.2, 1.3, 1.4%. So these are the ranges. Most soils of developing countries in Africa, South Asia, Central America, the Caribbean, these soils are degraded. Their organic matter content is about 0.5%. and therefore their productivity, their use efficiency of inputs, their quality of biomass, fodder and feed produced is not very good. And this is where the carbon farming and sustainable development goals are essential to alleviate the problems faced when the soils are degraded. And that needs transformational agriculture. The Green Revolution, which was seed-centric and based on fossil-fueled inputs, fertilizer, pesticide, tillage, irrigation, is feeding 90% of the world's today's 8.2 billion people. And whatever was done in the 60s under the leadership of greatest scientists like Dr. Borlaug, Dr. Swaminathan, and many others, was really no less than a great miracle, which saved hundreds of millions of people from starvation. Without the green evolution, the population which we have could not be fed, and some estimates only half could be fed. However, the dependence on fossil fuel-based inputs and their environmental ramification cannot be ignored. Whatever was to be done in the 1960s, we still need to produce food, but certainly without ruining the environment. It's not food or environment, it has to be both. I think that is the difference we are talking about. And in spite of all that green revolution, 1 in 11 is still prone to hunger. Today's information is 733 million people. That's where 1 in 11 comes from. And 2 to 3 in 7 are prone to hidden hunger, malnutrition, which is a serious problem for degraded soils. Therefore, the humanity is at a crossroads and faced with the challenge of reconciling the need for sustaining food production with the necessity of restoring degraded ecosystems and improving the environment through adoption of regenerative agriculture. Agriculture that restores soil health, improves the environment, mitigates climate change, increases biodiversity while producing safe and healthy food. That's the difference. That's really what we are talking about. Regenerative agriculture is a very talked about buzzword. It is not a practice. It is an approach. It's a strategy. It's a concept. It's an idea inspired by eco-innovation, powered by non-carbon, driven by a circular economy and green infrastructure, and supported by the re-carbonization of the terrestrial biosphere at the bedrock of sustainable development. We lost that carbon. Remember, 600 gigaton came from land? Somehow part of it, hopefully at least half, if not more, has to be turned back because that's the bedrock of sustainable development. Soil organic matter content is elixir of the life. Elixir is Arabic word, al-aksir. It is the recipe of life in the Arabic, elixir. And that is related to agroecology, application of ecological principle, very common book. It has 4 basic principles. Everything is connected to everything else. Mother Nature knows no mercy. There is no way to throw away. We talk about let's throw away where? And there is no such thing as a free lunch. Everything has a price. And the ecological price is much more serious than monetary price is. And it's the ecological price that we try to minimize in our agricultural, soil management, farming operation to produce food. The easiest concept is to create a positive carbon budget. That means the carbon by the way, this word budget itself implies that soil is no different than a bank account. Because if you want to increase your carbon bank account in soil, what you deposit in soil by many things must always be more than what you are withdrawing from soil by erosion, leaching, decomposition. This is sequestration. But when, unfortunately, the inputs of carbon into the soil is less than the losses, we are losing, depleting, degrading soil and taking carbon from the soil into the atmosphere. Most of these small landholder, about 550 million of them globally, unfortunately, have to, because of their poor resources, desperateness, following the extractive farming practices. A good way would be have improved varieties, deep root system, and that's again a difference between what was the original green revolution, have more grain than biomass. We need biomass equally importantly, and deep root system so the carbon can be distributed deeper in the soil. Association with mycorrhiza, rhizobia, so that P and N and other nutrients are absorbed more effectively. And this plant should be able to communicate with the manager via molecular-based signals, which are very specific for each stress the plant may be going through. Whether it's a drought stress, whether it's a grasshopper, whether it's a virus or fungal attack, whatever signal that we can detect, and intervention is made before serious harm happen. And this plant should be grown by no-till, by cover cropping, by mulch farming, and more importantly, by integrating with livestock and with trees. And this system will lead to high biodiversity in soil. It will create a disease-suppressive soil. It will enhance nutrient management. And if additional nutrients are required, if and when, they should be directly applied to plant roots in combination with water through drip fertigation, so that most of these nutrients are absorbed by plants and not leak out into the environment. So that is the way the science-based agriculture eventually have to look like. The technical potential of carbon sequestration of this approach in soils of the world is estimated at 2.5 gigaton petagram of carbon per year. And this between now and 2100, that's approximately 75 years, soils have a potential to store 178 petagram gigaton, vegetation 155, together 333, which is equal to drawdown of atmospheric CO2 about 157 parts per million. Therefore, if we can find alternative to fossil fuel and we can stop degradation of soil and water resources, the temperature control, abrupt climate change can still be managed judiciously and prudently by nature-based solution. And that is called nature-positive agriculture. Nature-positive agriculture means protecting, managing, restoring soil, strengthening biodiversity, improving water quality and renewability, adopting negative emission farming. Negative emission. Many times I say, I hear emission neutral farming or emission neutral agriculture. No. Agriculture is the only industry which have potential to be emission negative by sequestering carbon. Other industry can be emission neutral, but not agriculture. Agriculture has to be emission negative. Reducing import of chemicals using biostimulants, promoting biochar, circular economy, One Health concept, precision agriculture, and all of those, and producing more from less. Producing more from less is the key idea, and this is where AI can play a tremendously large and very essential role. Fertilizer, what I mean by producing more from less, fertilizer, we are using at present 200 million tons. And the use efficiency is very low. But if the use efficiency is improved, if the soil health is better, if precision agriculture is done, if AI can help decide the decision-making process, the fertilizer use can be reduced between 9,100 to 1/4 of what we are using. We still will need fertilizer to replace what is removed, but we cannot keep wasting with putting too much of it. Irrigated land area right now 350 million hectare. It can be 500 million hectare to overcome the issue of drought. The cropland area right now is 1.5 billion hectare. With proper soil management, with reducing food wastage, with change of diet, which is healthy for planet and healthy for people, we can reduce the cropland area between 920-100 to 750 by half. And conservation agriculture, which is only adopted 200 million hectare, should be adopted on an entire cropland area of 750 million hectare. And then as far as the grazing land is concerned, and I do understand that some ecosystem can only be used for grazing and not for cropland, but right now it is 3.7 billion hectare. I think we can do with 1,500, no more. And water use at present is about 3,150 kilometer cubed. Use efficiency is very low. Improve the use efficiency, and the water use can be reduced to 1/3. And with that mean, our crop yield can still be doubled, cereal yield, because of the better management of all the natural resources. And this is what we mean producing more from less. This is the idea behind returning some land back to nature. And I'm in this part suggesting half of the agricultural land, cropland and grazing land, go back to nature eventually. That will solve many problems that humanity is facing. Then this protection mechanism, we can adopt stewardship concept, that's religious, we can adopt legal approach or economic or combination of all that. And that brings me to the idea of legal part, rights of soil. Soil is a living entity, and like any other living entity, there must also be rights of soil and rights of nature. Being the essence of all life, soil has must rights to be protected, restored, thrive, and managed judiciously. That's rights of soil. Agricultural sustainability can be considered a three-legged stool. We have of this tool Clean Air Act of United States in 67, a Clean Water Act of 1972. How can you have clean air and clean water if there's no Healthy Soil Act? Therefore, policy interventions are needed to create Healthy Soil Act, which does not mean you're going to punish somebody who doesn't follow. It means rewarding those who do good agricultural practices. Others will follow eventually. Payment for ecosystem services I mentioned is $50 per credit. Again, you need a good way to actually calculate the social value of carbon. My estimate, we did it twice. It was in 2014, 2013 data, $35. Now 2018, since then, it's about $50 per credit. Where will the funds come from? The total amount required to implement what I just mentioned among 750 million farmers of the world is $100 billion per year. The COP21 in Paris suggested $1 billion per year. Now, many people think this is a lot of money. It's $12 per person. From that point of view, it's very small. Out of this, 70 billion should go to small farmers of the developing world, 30 to large farmers. No farmers is left behind. Everybody is paid for doing good things. Then the question is, where will that money come from? Fossil fuel exporting countries. Remember, we have a precedent. Tobacco smoking has caused cancer, and the industry that provided that tobacco have been considered to be responsible partly for it. So why not, when the earth is getting feverish, why should not oil exporting countries have some responsibility? Agro industries, of course, they should play an important role in providing the funding support, and the private sector. And of course, consumers, which is 8.2 billion people that I mentioned. I think if we want good, healthy, safe, nutritious food, we have very good responsibility that we must pay. The private sector can definitely play a very important role by promoting nature-positive agriculture, by increasing access to imports, by improving investment, and then, of course, finally, the soil stewardship. The religious leaders should also play an important part, and soil stewardship and care must be embedded in every fruit and vegetable eaten, in each grain ground into the bread consumed, in every cup of water used, in every breath of air inhaled, and in every scenic landscape cherished. With those economic, legal, and religious philosophy, it is possible to implement the concept of carbon farming and return some land back to nature. And by some mean, half of the land back to nature between now and the year 2100. Thank you.
Thank you very much, Dr. Lal. This is very insightful and inspiring. So we now have time for questions. Yeah, please feel free to speak if you want to ask questions.
Can I start off, Chang?
Yes, please go ahead, Gopal.
Yeah. Good afternoon, Dr. Lal.
Hi.
Thank you for an excellent talk. I just have this question. Say, probably you're aware of this 45Q tax credit that gives $85 per ton sequestered by industries and for direct air capture or for limiting CO2 emission from the industries. So how can we bring farming into that policy or for the tax credits? So what policy practices should be implemented for farmers or producers to gain a benefit of that?
Well, I mentioned Soil Health Act, and it does not exist anywhere. I'm very pleased to indicate that India has already drafted. There's a committee, I'm a member of it, the Soil Health Act, and that committee has a provision to pay farmers for ecosystem services. It's going to be finalized. The Indian Act is going to be finalized very shortly, like within the next month or so. The question really is, what's the mechanism? And of course, people talk about market trading carbon credit, buying and selling, and I have no problem with it. I think that's the way economics work, and economics is a good thing to follow. But here is a problem. In 1999, there was a Chicago Climate Exchange established. And Chicago Climate Exchange in 1999, you can look up CCX, it's called CCX. It was at $1 a credit. It went up to $6 a credit by 2006, 2007, compared with 30 euro in Europe. And that $6 per credit collapsed immediately to 20 cents. You can look up the history and see why did it collapse. There was no restriction. You could burn as much coal, as much oil, as much gasoline as you want. That was not the case in Europe. European country, each one of the 28, you have the upper limit. That means if you want to burn more, you have to buy credit. We did not have that. So unless that restriction, of course, the slogan recently has been dig, baby, dig. So how are we going to implement that? So I think finding alternative to fossil fuel and at the same time managing agricultural land properly and judiciously, which education could play a very, very critical role. Education at all levels, including kindergarten and children, those alphabet book I was talking about, primary and secondary school, general public and policy with regard to food waste, food security, nutritional value. And food waste, even in the US, is 30%. Keep producing more and more and wasting more and more and throwing more and more. Why produce it by spending so much resources? That's why I was showing. If you really use what we produce judiciously, then we do not need that much land. We do not need that much fertilizer. We will live in harmony with nature. And for that, we need a policy we don't have.
Thank you.
Are we done?
I think we have 8 more minutes.
Okay.
Do we have any other questions? I do have.
I have
Okay,
a
go ahead.
question about nice presentation. Thank you. I just wanted to know, in terms of carbon in the soil, there are differences among plants, and how much is known and what type of plants are going to be conserving more carbon? And is there some kind of selection that could happen in croplands that could help more carbon in the soil than other crops?
Yeah. Well, that's a good question. First of all, how much carbon can be sequestered in what soil? Soil does have a limit to how much carbon can be put into it. It's like your drinking water bottle. And how much water can I put in this bottle? As much I have drank already from it. So whatever I've consumed before is that amount that I can put back in generic condition. There are in some cases if soil had some limitation like Cerrado, Brazil, low pH, low calcium, magnesium, high aluminum, that under natural conditions restricted carbon stock. And if you can alleviate those natural conditions, carbon stock can go beyond what was under natural condition. Desert climate the same way. If you irrigate more water. So those are the practices which are site specific, but the goal is to know how much is being removed by decomposition, by erosion, leaching. Those are the three main categories. And we must add more than that. And that will increase the carbon. Remember, I had a balance. Most of the time, we do not have that statistic, that data. That requires local research. And that is what measurement, monitoring, verification. This is where AI and other technique could play a very, very important role. But soils are very highly variable, and their rate of sequestration varies very widely on the basis of climate, soil depth, clay mineralogy. Climate is the best soil to store carbon are those in cool, humid climate. As far as the organic carbon is concerned, organic carbon storage is less in a hot, dry climate. Inorganic carbon can be more in hot and dry climate, but not organic carbon. So there is not much research on inorganic carbon, but I think there's a lot of scope in the desert area to also store carbon, not through plants, but through abiotic processes. And there are some abiotic processes where it can happen.
Thank you.
Thank you. And we also have a question from the chat from Jose. And so he asked, how good are the current methods to estimate effects of land use change or land management on carbon sequestration? So measuring the actual changes in the field will be very complicated due to soil heterogeneity.
Well, as of now, beginning since 1850, we have been monitoring carbon in a very, very laborious method. It's called dry combustion or wet combustion method. That taking the soil sample to different depth, measuring the bulk density, but measuring bulk density is very important because you are converting percent to ton stock, and that requires bulk density measurement. But I think that method of measuring carbon should be replaced by something which can be through satellite imagery, through remote sensing. I have a student postdoc with me, and she, with the help of Microsoft, have been developing a methodology similar like your cell phone, pointed to the soil under field condition, and it can give you approximately moisture content. and moisture content, of course, depend on the organic carbon content. So you calibrate those devices. So things of that nature, the Thermo's National Lab had a device called LIBS, laser-induced breakdown spectroscopy, which also mounted on a tractor and driving the tractor at a constant speed could tell you over time, as you drive tractor on a given spot today, come back after 6 months or 5 years, it can estimate carbon, I believe, to about 40, 50 centimeter depth. So modern innovations are happening so that you do not have to go through the laborious process. The other part, which is, I think, important, many people say we have to monitor how much carbon changes have happened. Yes, at some few places, we must validate what we are estimating. But eventually, if the carbon farming were to become a practical concept, translating science into actual action, we have to go by land use practice. If a farmer is doing conservation tillage, we know how much carbon is being sequestered on the basis of the previous knowledge of experiment. If farmers do conservation tillage plus cover cropping, we also know that. If farmers are growing conservation tillage with cover cropping and rotation with grazing or with agroforestry, those approximate estimates are known. So pay farmer on the basis of land use. And how do you monitor land use? By remote sensing. We had a precedence of that, if you remember, set-aside land program. Highly erodible land in the U.S. were required to be set aside, leave them for nature. That's what I was talking about, return land back to nature. And how were they paying farmer if the land was declared as highly erodible land because of the basis of soil or texture? They were taking picture, and if the farmers are not plowing, not growing any crop, pay them what they would have got by growing crop on it. That was very successful. That act came out in 1987. So something like that can be implemented.
Great. And speaking of the incentives for farmers, so there's another question, which is our last question related to the farmers, like how we can develop like strategies that we can win farmers' interest with the long-term effects of carbon sequestration. It takes like very long time, like 20 years, for example, for significant changes.
Yeah, I think the first thing to really is there are a lot of companies coming up, and they are companies which say we can trade carbon with you, and farmers do not know which company is good and which is not, and the price range varies very widely, from $10 to $50, and so at present the situation of making sure that the farmer trust is reestablished, because trust, if they do not trust, nothing can be implemented. And that means a system has to be developed by which the farmers who adopt a certain practice for a long period of time will be rewarded because they are doing good things. And that system, I mentioned set-aside land. That was a system which worked out very well. And pay farmer the societal value of carbon. So some pay $10, some pay $15. If the societal value is 50, why would farmer accept 15 rather than 50? And then why would a farmer trust people who approach them? So I think we have to develop a system of paying farmer honestly, fairly, justly, transparently. 90% of the total expenses, in my opinion, that we set aside through some legal issue, through some governmental programs, should go to farmers. 10% maybe to the arbitrator, the companies.
Wow, thank you so much, Dr. Lal, for sharing your expertise and time for us. And thank you for everyone for joining the seminar. And we look forward to seeing you in future sessions. in the IFAS AI seminar.